So, 2.5. Who started the homework, just to show of hands? Okay, 2 people, perfect. So, a spring mass system, meaning there's no damper, right? That's the first thing, is that if they said spring mass damper, you know there'd be damping, there's no damping in this problem. The spring mass system is driven from rest harmonically. What's harmonically mean?
Sinusoidal.
Sinusoidal. Harmonic means sinusoidal. Such that the displacement response exhibits a beat of period 0.2 pi seconds. So this is a period that's given to us related to the beat. And then it gives us the period of oscillation, which is 0.02 seconds. So we have, I'm just going to write down T beat. That is 0.2 pi. And you have T oscillation, which is 0.02 pi. Those are seconds. And we want to find the natural frequency and the driving frequency of the system. Now, just from a conceptual standpoint, our answers for the driving frequency and the natural frequency, what should we expect about them considering we're beating?
Really close.
They're close together, right? Because we know that we have beating if the frequencies omega and omega n are nearby each other. So that's kind of what we're trying to do with this problem. So I'm going to pull this up. Is this okay? Everybody kind of get a feel for this problem? And if not, check the textbook in on Canvas. So let's draw a picture of beating and try to understand what's happening in this problem. So if you had a system that's beating, you have something that's growing, and then it's decaying, and then it's growing, and then decaying, and so on. I know that's not a horizontal line, but whatever. So we really have two types of frequencies at play in this problem. We have the frequency associated with the actual movement of the object. That's the little ripples here. Up, down, up, down, up, down, up, down, up, down, and it's getting bigger, 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 smaller, smaller, smaller. So do you think, if you had to pick between these two periods, 0.02 pi and 0.02 pi, which one would be the distance between, let's say, two consecutive peaks?
T oscillation.
Yeah, the one that's smaller, right? 0.02 pi is a smaller number. This is less time. So right here is 0.02 pi. This is your T oscillation. And if you think about it, the mass is oscillating back and forth at some frequency. That is this frequency. The amplitude is changing, sure, but it's still oscillating back and forth at that frequency. That make sense? So that's T oscillation. Now, if you look at the envelope of this, you'll see that you have this kind of sinusoid whole thing happening, again, which is our change in volume. Wah, 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 wah. That was that video, right, that we talked about. Now, if you write down the formula for beating, which is, I don't have it in front of me, I think I know it. It's something like, I don't remember what the amplitude is, but it's sine of omega n plus omega over 2 times sine of omega n minus omega over 2 of t. I think that's right. Anybody can confirm that for me. I wrote this out, so it might be good. Yeah, that's right. So, when it comes to this equation, there's an amplitude in the front that dictates, it's based on the force and stuff like that. But in regards to the behavior of the sinusoids, we have omega n plus omega over 2. If you had to think about high versus low frequencies, is this going to be a very high frequency or very low frequency? High, it's very large, right? I take these two, add them together. That's going to be a high frequency. So this is a high frequency. So do you think this is going to be related to the oscillation or the beat? Oscillation, that's the thing that is changing more often. Like this is one cycle in this amount of time. If you look at 1 second, you had, in this picture I drew, maybe 10 cycles in that second, versus the other one is just half a cycle. So this is related to the oscillation. This is the oscillation. So we were given the period of that. If we have the period, what do we know?
Frequency.
Frequency in hertz, right? They're reciprocals, right? So we know that. Now, in regards to the beat frequency, this is more of a definition, because the period of, or rather this giant thing here, is actually not considered the beat frequency. The beat frequency by definition is the subtraction of those two. Basically, every time you have, if you think about it in terms of what's happening with the sound, this is low, it gets high, it gets high, it gets low, it starts over. So really, this here is the period of the beat. It doesn't seem like it based on the way the envelope is drawn, the dashed line, but if you just think about it from a physical perspective with the loudness, this starts low, gets high, gets low, repeats. So we define this omega n minus omega as the beat frequency. That was the definition we discussed in class. Omega beat is omega n minus omega. So this T beat was 0.2 pi seconds. That was our beating period. Does that make sense conceptually? Right, we have both these things happening at the same time, the many oscillations, and then the change in amplitude as a function of time, where it restarts there, and that's considered a beat. Is that okay? Doubts? Peter? Okay. So, really what I can say is that I have omega n plus omega over 2. This is omega oscillation, right? Because this is the high frequency thing. And then I have omega n minus omega, which again is a definition. This is omega beat. So again, that 2 in the denominator is basically showing us this giant envelope, but in regards to the physical nature of the problem, only half of that is considered the full beat period. So omega oscillation, this is the same as 2 pi f. Oscillation in omega beat is the same as 2 pi f beat. Omega is 2 pi f, right? That's what the definition is. And from the problem, we can find what the two f's are because we're given the period. It's the reciprocal of those numbers. So if we look at this one, let's say, this will be omega n plus omega over 2. That's going to be 2 pi 1 over t oscillation, because the frequency and the period are reciprocals of each other. And that's why they give us a pi here, because we end up canceling pi's out, right? So you don't even need a calculator for this problem. Well, maybe you do for the decimals, but in general, the pi's cancel. This would be 2 pi 1 over the oscillation period, which is 0.02 pi. And that's 100. So omega n plus omega over 2 ends up being 100. Because 2 divided by 0.02 is 100, and the pi's cancel. So that's one equation. we can come to our second equation and say omega n minus omega is 2 pi 1 over TB. That's the definition. TB is 0.2 pi. So we get that omega n minus omega is 10. Now we have a system of equations we can solve. We have two equations, two unknowns. So if I bring the 2 over to the other side, I don't know if the camera can see me. Can it see me, Charbel? So omega n plus omega, if we bring the 2 over is 200. Then you have omega n minus omega is equal to 10. We can add these equations together to eliminate the omegas. So we get 2 omega n is 210. We get omega n as 105 radians per second. And then if we plug that back into one of these equations, we end up seeing that omega is 95 radians per second. And that's the answer to the problem. So again, you'd have this type of equation on a formula sheet that shows you the beat pattern or what you expect to it. The frequencies are close. So recognizing that the period is related to frequency, knowing the definition of the beat frequency, again, it's not this whole thing inside of the sign, because this whole thing is referring to this envelope. But in regards to the beat, when the loudness changes, this is considered one period. So it ends up being just the numerator of that expression. And then you can solve for omega n and omega with the system of equations. Good morning. Questions about this? Is that clear up here?
I think so, yeah.
Cool. What else?
2.27.
What'd you say? 2 point what?
2.7.
2.7?
Yeah.
What was it from?
You do that one yet?
That's it. That took me a while.
You want me to do the hard one?
Mm-hmm. That's true.
Can I erase this? So, I'll pull down the screen again for people who haven't seen the problem yet. Take a second to read this while I erase. So we have a pendulum that's pivoted at point O. You see that here's where point O is. This is the fixed position. And it wants us to calculate the damped and undamped natural frequency of the system for small angles. Assume that the mass of the rod, the spring, and the damper are negligible. What driving frequency will cause resonance? So, just thinking ahead, they're asking for the damped and the undamped natural frequency. What is the relationship between those? Or rather, what's the natural frequency first? Square root of k over m, which we can get from, or g over l, which we can get from the differential equation. If we have the differential equation, and we convert it to monic form, we know that the term that's with the x, or with the theta, not the theta dot, not the theta double dot, is the natural frequency squared, right? If I were to write that on the board, you know, x double dot plus 2 zeta omega n x dot plus omega n squared x is equal to, you know, some force or whatever, we know that omega n is in that differential equation by default. So if we were to derive the differential equation, we can get this from it. That makes sense? Okay? That's how you find omega n. Omega d is based on what?
Damping.
It's based on damping. Omega d, the definition, again, and this is assuming it's underdamped, which it must be if we have a damped natural frequency, is omega n the square root of 1 minus zeta squared. So once we have omega n, we need to find zeta. How do we find zeta?
Using
Q
the
zeta
C over
omega.
N.
Yeah, you use the other term in the differential equation to find zeta. You already found omega n. So now you can plug that in there to get the damped natural frequency. So that's the first part of this problem, finding both the natural and the damped natural frequency. The next part says, what driving frequency will cause resonance? So when will that occur? When it's equal to omega n. So once you found the natural frequency, you're basically done, because that's going to be the frequency that drives it to cause resonance. Everybody understand this problem so far, what our game plan is? Like when I solve these types of problems, I like to think ahead and be like, what do I need to do? Because there's a lot of things we can do. There's a lot of equations in this class, right? But in this system in particular, we have a pendulum. So we have to figure out a way to find the differential equation. And we have a few ways of doing that. What are some of the ways we can do for finding the pendulum differential equation?
What's wrong?
We can do Lagrange. Now, there's one caveat to that. What makes Lagrange, based on what we've talked about in class, not desirable for this problem specifically?
The damper?
The damper. When we talked about all of our energy methods, we assumed that there were no losses, there was no damping. But because we have a damper here, that's going to make it difficult for us to use the equations we've discussed already in class. So that is an idea though, we can do that, but we're not going to. What else can we do?
Sum of moments.
Sum of moments, which is exactly like the problem you had on your exam. Where you have a pendulum, you have to find the moments about a point, and go ahead and use sum of moments as J theta double dot. So let me go ahead and draw this on the board. So here's our pivot point. This is O. Let's see. This is K. Here's our point mass M. And there's a force that is acting across F of T. And they give us some lengths. This is L1. This is L2. They give us numbers for these, but we'll plug them in at the end if we want, but I'd rather just go ahead and derive this from the variables, and they call this L. K, L1, L2, L goes from the pivot point to the mass, and C. And that's everything we need for the problem. So maybe we'll draw a picture to kind of help us visualize what's happening with this. What direction do we expect the mass to go?
To the left.
Left, because of the force, right? The force is going to push it to the left. So that means that this whole rod is going to go clockwise. So if I were to draw this, I might have, this is my pivot point. And because we have pushed it to the left, we end up creating an angle. Let's call that angle theta. What's this angle?
Same angle.
Huh?
Which angle?
This angle.
That would be theta.
It's also theta. Correct. Okay, I'm gonna make this a little bit longer so we can have room to write. And again, this is pivot point O. So, we want to sum the moments about point O. We need to find which forces are contributing a moment. Let's go ahead and look at the possible forces in this problem. What are some forces that are present in this problem, Dylan?
The mass.
The mass has a force. Let's go ahead and draw that mass going down. This is mg. That will provide a force. What else provides a force? The damper provides a force, and the damper is L2 away from the pivot point. Now, what direction is the damping force going to act? Is it going to act to the right or to the left?
To the right.
To the right. It's trying to resist the motion. So we're going to have a damping force here. I'll call this F, I don't know, damper, if you want. And to this point, this is L2.
And we also have our spring force. Right?
We have our spring force, which will be pointing to the right or to the left? To the left, right? If I'm twisting it this way, this spring wants to go back to equilibrium. We'll end up having a force that goes this way. This is F spring. And then this length here we said was L1. Is that everything?
The force.
The force itself, that's causing a moment. I mean, that's what's causing the rotation to begin with, right? That's definitely going to have a moment. This is F of t. And we know that this whole distance from here to here, that's L. We'll make sure I have that correct. Looks like it's right. Yeah, okay. So we have to go ahead and find all of these moment contributions. So we're going to sum the moments. Let's go ahead and let's sum the moments about point O. And our equation says that's equal to J about point O times theta double dot. So we have to sum all the moments. Do any of them cancel out? And what do I mean by that? When would that happen?
When they go through the
If it goes
point.
When they go through the pivot point. If they go through this point, that's not causing rotation, like a reaction force or a tension. In this problem, based on the forces we wrote, do any of them go through the pivot point? No. So we have to calculate all four moments, can't speak. Okay. So let's go ahead and do these one at a time. Remember, the force is based on the moment arm. The distance it is away, the perpendicular distance it is away from point O. So let's look at mg. If you look at mg, mg is going down, which means the perpendicular distance from O will be something horizontal, like this. So what will that be?
L sine theta.
L sine theta. Now, I didn't mention this enough, or really at all, when we did pendulums. I want to talk about the signs of moments for a second. So if this guy is going to the right, that is the direction that the angle is being formed in. That's a positive theta. Is mg working to try and increase theta or decrease theta?
Decrease.
What's that?
Decrease.
Decrease. So is it negative or positive moment?
Negative.
It's negative. It's trying to limit the motion. So this would be minus mg, that's the force, times the moment arm, which we said is L, this giant L, sine of theta. Okay? Easy? Okay? Let's do this force next. So this force, is that going to be a positive or a negative moment? That's positive. It's the one that's causing theta to grow. So this will be a plus. This will be the force, say F of t, times the moment arm. Again, this is the perpendicular distance from this force to point O. So what will that be?
L cosine theta.
That's L cosine theta, this distance, which would be this L times cosine theta. So F of t times L cosine theta. Okay? Okay? We don't know what F of t is. I don't know if they gave it to us in the problem. Or we'll just leave it as F of t for now. Okay, let's do the damper. Is the damper going to be a positive or a negative moment?
Negative.
Negative, it's trying to restrict the motion. This would be negative. What's the force of the damper going to be?
CX dot.
Cx dot, right? I'm going to write it in terms of x, but we will have to go ahead and replace that with theta after. But for now, let's just leave it as Cx dot. So this would be minus the force of the damper, which is Cx dot, times its moment arm. So again, this is going across. We're looking for the perpendicular distance. What will that be?
L2 cosine.
L2 cosine theta. This is L2. Cosine theta is that perpendicular distance. So this is L2 cosine theta. Okay? Okay? What about the spring? The spring is causing a positive or a negative moment.
Negative.
It's negative, it's restricting the motion. Because again, this theta here is going to the right, the spring is trying to pull it to the left, so this is a negative moment. What's the force of a spring?
X, KX.
This is Kx,
It's like XK.
Jesus Christ, man.
Xk, yeah.
XK.
But it's not wrong.
It's not wrong, but it's weird. Kx times the moment arm, which is what? L1 cosine theta. And those are our 4 moments. We do it slowly, right? We check to see first if the force goes through the pivot point. If it doesn't, or if it does, there's no moment. If it doesn't, we have to consider it. We draw our vectors and ask ourselves for the sign, is it helping or hurting the rotation? If it's helping, it'll be a positive moment. It'll go in the direction that is increasing the angle. And then once we know the direction of the force, we try to find the perpendicular distance. That's our moment. Let's think back to Nora. I'm sure Nora said something about this at some point, screaming at you, R cross F, or whatever, you know?
Yeah.
Same type of thing.
Sending this to Nora.
Huh?
We're sending this to Nora.
Send it.
You make fun of it.
He makes fun of me, it's fine. So, this will be equal to J naught. J naught, remember,
JC.
by definition, I'll just write this down here for now. J naught is the moment of the mass moment of inertia about the center of mass of the problem. This is a point mass, so what's JCM? 0. Plus m times the shortest distance to the pivot point from the mass,
So M squared.
which would just be L squared. So it's going to be ML squared is J naught. So this ends up being equal to ML squared theta double dot. We'll deal with the x's in a second. Let's go ahead and try to bring everything over to one side. I'll leave the ML squared theta double dot as being positive. So I have ML squared theta double dot. We have plus all of these terms brought to the other side, plus MGL sine theta plus CX dot L2 cosine theta plus KXL1 cosine theta. And if we want to leave the force on the other side, again, it's our forcing function. That's typically on the right side of a differential equation. that will be f of t times L cosine of theta. Is that okay?
Do we divide by ML squared or?
Let's do that. Let's also do our small angle approximation. We're gonna have to figure out x before we divide by ml squared. Well, if we do our small angle approximation, what happens to sine?
Theta.
That goes to theta.
Don't you want to do x before small angle?
Oh, yes, you're right. I want to do x before small angle. Thank you. Because we're gonna have x in terms of theta, so we don't want to do any small angle stuff yet. Thank you. So, let's go ahead and look at this rotation again. Let's look at this x. I should probably differentiate these x's, honestly, because this one is based on the spring's displacement. Maybe I'll call this x spring, and I'll call this xd for damper. Sorry about that. I'm just going to fix that because they might have different values. You're each deflecting different amounts, right? You're different distances away from the pivot. So looking at this picture, what do you think x spring is going to be?
L1 sine theta.
L1 sine theta, that's correct. We'll say that x spring is L1 sine of theta. Let's double check that. This distance here is x spring, this distance. So that will be the sine of theta times L1. What about F damper? What would its deflection be?
L2 sine theta.
That's L2 sine theta. That's correct. That's L2 sine theta. So we'll say that XD is L2 sine theta. Okay.
But isn't it x dot?
Yeah, we'll see that in a second, right? So let's go ahead and use our small angle approximation. This will be L1 theta. This will be L2 theta. And now if I do x dot, you will end up with L2 theta double dot. Or theta dot, sorry, not double dot. L2 theta dot. You see that? If you did the small angle approximation first, or rather you took the derivative in terms of this without the small angle, you'd have L2 times cosine theta. Cosine theta approximately goes to 1. Then you don't have a velocity that really makes sense anymore. You'd have it being 0 at the end of the day. So you want to do this now to ensure that you're considering the angular velocity that's associated with the pendulum. Okay? So now we can plug all this stuff in. You get ML squared theta double dot plus MGL sine of theta becomes theta plus CX dot. If it's a dot, that's the damper. XD is what I called it, XD. Plus CXD dot, that's L2 theta dot, times cosine theta, times another L2, sorry, times another L2. Right, XD dot is L2 theta dot, that goes there, there's two L2s. Times cosine of theta is 1. Plus K times X, this is X of the spring. That is L1 theta multiplied by another L1, gives us L1 squared theta times cosine theta is 1. That will equal F of T, L, and then cosine theta becomes 1. Any doubts about this? Okay. Now, in order to find the natural frequency, I recommend converting to what?
Monic.
Monic form, because if I divide by ml squared, then I'll be in this exact form over here where we have our natural frequency already there. So we'll have theta double dot. I'm going to rearrange this a bit. I'm going to put this one first. because of the fact we want to write it in order of decreasing derivatives, plus CL2 squared over ML squared times theta dot. And now these two combine, because they're both theta, that will be plus MGL plus KL1 squared, all of that divided by ML squared theta, and that equals our forcing function on the right times the length. Did I mess something up?
And
Do you
then
not divide
divide
that
by
by
LP on the
L
bottom.
squared?
Oh, thank you, that's correct. So this would be f of t divided by ML squared, thank you.
And
The L's will cancel, right? So that would end up being n out. Thank you. That make sense? Okay. So what is our natural frequency?
Square root of.
That thing.
That whole thing.
Yeah, exactly. So, omega n is the square root of that term, again, which is MGL plus K L1 squared over ML squared. That is our natural frequency for this problem. MGL is KL1 squared over ML squared, yep. So if there was no damper, remember, the natural frequency is just based on K over M. If the damper didn't exist, and it was just this mass going back and forth with the spring up here, that is the frequency that it would oscillate at, the angular frequency that it would oscillate at. So now we have to find the damped natural frequency. Which is omega d. That's omega n, the square root of 1 minus zeta squared.
You gotta find zeta.
You gotta find zeta. So again, this guy over here, this was omega n squared, while this guy over here, this was 2 zeta omega n. Is that okay? So we have C L2 squared over ML squared. That whole thing is equal to 2 zeta omega n. We can then solve for zeta by dividing both sides by 2 omega n. And of course, there's some algebra there. You can plug in what omega n is here and then flip things around.
Can we leave it like that on the homework, or do you want it like simplified?
You should leave it, please.
Sure, you can leave. So, then we would say omega d is omega n, the square root of 1 minus that term squared, c squared L2 to the 4th, divided by 4 m squared L to the 4th omega n squared. And that's our damped natural frequency. And that's the problem. Doubts about that? Again, a lot of these problems look scary at first, but break it down into a free body diagram, understand the physics with the moments and the forces, and then sum the moments up if you ever have some sort of rotating problem. If it was a non-rotating problem, you'd sum the forces up. It's the same deal. The vibrations part is really recognizing the mnemonic form version of this differential equation, where you have this as the natural frequency squared and that being based on the damping ratio. Hey, does that make sense?
No, yeah, figure it out.
You said you'll figure it out.
Yeah.
What else? Anything throwing people off right now, whether in the homework or in class? Hi.
Can you explain where you got the square from, like ML squared theta dot?
This one?
Yeah.
That's our J, right? So our equation for the moments is to say that the sum of moments, that's J naught theta double dot. So the sum of moments were these guys, all four of these, those are the moments. J naught is the mass moment of inertia about some pivot point, O. And the definition of J naught is based on the parallel axis theorem. Where here's our problem, here's the mass, and here's the pivot point. We'll neglect all the other forces right now, but there's a spring, there's a damper, whatever. The only mass in the system is at this point mass. That's the only mass present. And it's a point mass, which means there's no distribution of mass. It's just all dense together in one spot. So that means that JCM, and again, this whole concept of J is how the mass is distributed about something in regards to rotation. So for this, if we look at the center of mass of this whole system, it's at the point mass. There's no other mass in the system, so it's right here. And because it's a point, there's no ability to rotate the mass. Sure, in regards to the pendulum, the whole thing can rotate, but this mass specifically, like if I just had a dot, I can't really rotate it because it's just a point. So we say that its mass moment of inertia about its center is what?
0.
0. So this is 0. And then we say that this is going to be m times this d here is the distance away from the pivot point, which in this problem happened to be L. So this is ml squared, which is where this comes from here, ml squared theta double dot. So that's the sum of moments is equal to that. That's where that comes from. Answer your question?
Yeah.
Cool. What else? Peter, do you have a third problem? If you have problems, man, I'm happy to do them.
I have plenty of problems. It's 2.9.
Which one is it? So for 2.9, you have a force system. You have a force over here, 10 sine of 10 t. Is this 10, is this omega n, or is this omega?
Omega.
That's just omega. Omega n has to do with the mass and all the stuff over here. This is an external force. That's omega, the driving frequency. It says you have this system and you want to calculate the response, meaning find x of t, given the values of k that are in series, which means they share the same force or the same effort, because both of these, like tension in a rope, they both feel the same force, but they can experience different displacements. So these each have a different spring constant, K1 and K2, you're given a mass, and it says the system's initially at rest, which means that your initial conditions for the problem are 0. we want to write the equation of motion, so we have to find our differential equation, and then go ahead and determine what x of t is, so we solve the differential equation. So let me write down some of the givens from this problem so we have them. So we have K1, K2, and M. M is 89 kilograms. K1 is 100 newtons per meter, and then K2 is 500 newtons per meter. And it was 10 sine of 10t. That's our f of t. 10 sine of 10t. Can I pull this up? Okay. So go ahead and take a second. I want you to try to find a differential equation for this problem. Now, instead of doing sum of moments is J naught theta double dot, there's no rotation, what do? F equals ma, thank you. F equals ma. That was a tough one. So we'll sum the forces for that problem instead of equal to mx double dot. So I'll draw on the board at least. Now let's go ahead and find our equivalent spring as well. M, K1, K2. This is, I'll just call it F naught sine omega t. And for me, you know, I don't love using numbers right away despite the fact we're given it. Because if I just say F naught is 10 and then I convert it to mnemonic form and then write it as some other number, and I just have a bunch of numbers at the end, and I get it wrong, it's hard for me to figure out where that error occurred. Because there's just so many numbers. But if you're looking at variables, at least you can kind of follow your steps and be like, okay, I divided by this here. Oh, I forgot to square that. That's why it went wrong. But if you plug in numbers right away, it gets messy, especially if you make a calculator error when you're doing your homework. So go ahead and take a few seconds to find out what the differential equation is.
What are we trying to solve?
We're trying to find the differential equation first, and then after that we want to find x of t. So the solution to the differential equation. Yeah.
In the solution x of t, is there still a transient and steady state response, or just steady state?
So there is a steady state response only,
Yeah.
but the driving frequency and the natural frequency are still present in that response. So when you go through your derivation, if you were to derive it, you have to assume non-zero initial conditions to get the correct answer. Then at the end, you plug in specific cases where x naught and b naught are zero. We'll go ahead and start this though, at least just finding the k's, right? So k, I can do, they're in series, and if springs are in series, you'll have this reciprocal nature, they do not add. Another way you can write this too, which is the way I typically remember it, is product over sum.
That's what I do. Always get it wrong.
Which is valid when you have two springs in series. So if you found a common denominator and added and flipped, then you would get this. So we can find that number now if you want, just so we have KEQ done. We don't need to write K1, K2 over K1 plus K2 the whole time. So that will be 100 times 500 divided by 100 plus 500. What's that?
I got 83.3.
I think you're right, that sounds familiar. 83.3 newtons per meter.
I know.
So I have that number down, I'll call it KEQ, for K equivalent, 83.3. So if we're the sum of forces about this, and say this is equal to mx double dot, we'll assume that this is the positive direction. So you have F naught causing that motion, that would be positive, minus what?
Yeah. K equivalent.
times x.
KQ times x, right? That's the whole point of finding the equivalent stiffness, is that you can just write this as KQ times x. That'll equal mx double dot. And then when you bring everything regarding the system over to the one side and leave everything external on the other, you end up with our standard differential equation.
And we will turn that to monic form.
You can turn the monic form if you'd like. So if we do that, divide by m, you get x double dot plus k over n is omega n squared. X, and that will be little f naught sine omega t. Maybe I'll calculate what f naught is, just so I have it. That's big F naught over m. What's big F naught in this problem?
10.
10, this 10. Divided by the mass, which was 89.
You're 0.112.
0.112 newtons per kilogram is little f naught. So just keep that handy. And then we can calculate our omega n squared if you like. That's KQ over m. KQ is 83.3 newtons per meter divided by the mass, which is 89 kilograms. That ends up being 0.968, I think. Is that right? Radians per second. So that's omega n squared. Oh, that's not radians per second. That's radians squared per second squared. I'm gonna leave this 0.968, so those are double units. Oh no, sorry. This is omega n. Sorry. Radians per second.
This guy. Can you tell us what you know? This guy.
What? We didn't say that. Is that what we got? Okay, making sure. So, there are equations for this. We can just write out what the answer is. But again, I just want to show you how to do that so you have those techniques available to you. When we solve a differential equation, we'll do homogeneous. First, and again, there's no transient here because the initial conditions are 0, but we have to consider both of them in our total solution. So the homogeneous will be when the right side is 0, and this is really what we had on the first day of class, right? That's our original differential equation. And there's a bunch of ways to write this. We can use an exponential, we can use one sine wave with a magnitude and a phase, or we can use one cosine and one sine wave. They're all equivalent. We've shown that in homework that you can mathematically convert between them all. So I'm just going to write out what this answer ends up being. We can write this as A1 cosine omega nt plus A2 sine omega nt. That is our homogeneous. That's one way of writing it. That's the way the book does it, which is why I'm sticking with it. But you could have written this again. You could have assumed an exponential solution, e to the lambda t. Find what lambda is. You would get two repeated roots, or not, so you get complex conjugate roots. You get plus or minus j omega n. You can convert those complex exponentials to sines and cosines. You get this. And you can use trig identities to convert between this and sine omega nt plus a phase phi. They're all equivalent. Any confusion about that? Okay? Okay. Particular. Same thing, except now we have
Forcing.
the forcing function on the right, which we wrote as f naught sine omega t. We can solve this in a bunch of ways. We've learned a bunch of ways on how to solve this. We can assume a solution. We can do the complex response method, where we assume a complex exponential and then deal with complex exponentials the whole time, do the F or F. Or we can do, what was the last one? Laplace transforms. You do Laplace transforms, take the Laplace of both sides, find the transfer function, take the inverse of it, and then you get your answer. They're all equivalent. For this, because there's no damper, it actually ends up being pretty simple. We'll just assume that this is some amplitude times sine omega t. Do we expect a phase shift between the force and the displacement?
No,
No, why not?
there's no damper.
There's no damper. The damper is the thing that provides the phase shift. There's no damper in this problem, so there's no phase shift. We will have our amplitude be some capital X. We don't know what that is. We have to find that. But we're going to assume that the sine, the oscillation will be of the same frequency of the force. And I guess I have to be careful. There may be a phase shift. When would there be a phase shift, and what is the phase shift? Dylan.
Is it if R is bigger than 1?
If R is bigger than 1, then what is that phase shift going to be? 180. That's correct. Killing it, man. I'm so proud of it. My heart is just okay. I know. So x dot is x omega cosine omega t. And you have a damper. This is when this becomes annoying because you have an x dot term with a cosine. You can't cancel things as easily. That's frustrating, which is why this isn't the best way if you have a damper. But if you don't have a damper, what's nice is that you end up with a bunch of signs that all cancel. You see that? Plug that in. Negative x omega squared sine omega t plus omega n squared x sine omega t equals f naught sine omega t. All the signs will cancel. So I'll just write this as negative x omega squared plus omega n squared x is equal to f naught. And we get our amplitude x as being f naught over omega n squared minus omega squared. And that's what we've seen when we did our derivation in unit set 7 with undamped systems. We see that if the driving frequency is smaller than the natural frequency, this is positive, they're in phase. When the driving frequency exceeds resonance, meaning it's bigger than omega n, this denominator becomes negative, causing x to become negative. Now they're out of phase by 180 degrees. Dylan.
What would happen if we did have a damper?
If we did,
Yeah.
well, that's what I'm saying, that changes this. We end up with this having the square root in the bottom, omega n squared minus omega squared, plus 2 zeta omega n omega squared, it's something like that. So we have a zeta there that actually limits the amplitude of the motion. So we'll never actually go to infinity, it'll peak out somewhere because of the damping. And depending on how damped it is, that'll dictate how high that amplitude is. That's a good reminder.
Yeah, I remember, because whenever the c was 0, it canceled out that term.
Yeah, exactly. So that means that our particular solution, again, was this x times sine omega t. So that is our particular, and now we will find our total by, you know what? Adding them. We'll add the homogeneous, we'll add the particular together to give us our total solution. X total, that will be A1 cosine omega nt plus A2 sine omega nt plus this. Sine of omega t. So we see that the homogeneous is just based on omega n, because there's no forcing function in that situation with the homogeneous. There's no omega present in this equation. The only thing that's there is omega n, which is why the homogeneous just depends on omega n. While the particular depends on omega since it's dependent on the force. That's the whole point. So let's go ahead and just take the derivative of this. So we find x dot for our initial conditions, x dot of the total. That will be negative A1 omega n sine omega nt plus A2 omega n cosine omega nt plus this coefficient times another factor of omega. Cosine omega t. So we can plug in time equals 0 and relate this to some x naught and v naught, and we'll learn how the total solution is impacted by the presence of these. So if I do x total at time equals 0, this is x naught, that will be just A1. The sign terms go away. This is just A1. X dot total. That'll be A2 omega n plus x omega basically. The F naught over the squared subtracted. The A2 omega n plus F naught omega over omega n squared minus omega squared, that whole thing is equal to v naught. That's the initial condition for velocity. Leave those numbers up. So if we were to go ahead and bring everything over and solve for A2 in the way I defined it, this would be V naught over omega n minus F naught over omega n squared minus omega squared times omega over omega n. This was originally A2 omega n. I divided all those terms by omega n and did a little bit of algebra to isolate A2. And if you look at that bottom equation and here, you'll see they're the same, just divided by omega n. This is an A2. Any doubts about this? I expect you to be able, like that first question on the test, if I give you a critically damped system, you should be able to plug in initial conditions to find the unknown coefficients. A little bit of algebra, but conceptually, I think that makes sense. I hope it makes sense. So based on our total, this will be A1 cosine, that's X naught cosine. Omega nt. Erase the rest of this stuff. Plus A2 sine. So A2 is this whole thing here, V naught over omega n minus F naught over omega n squared minus omega squared times omega over omega n, that's sine omega nt, or sorry, cosine. Wait, sine,
Maybe
looking
sine.
at the top one, yeah. Plus F naught over omega n squared minus omega squared times sine of omega t. So you see that this term here doesn't actually depend on initial conditions, but it comes from solving the differential equation, assuming a general form, and then when you plug x naught and v naught in, you have this remaining term. It's not just going to be equal to this. You can't just say that the total solution is this with zero initial conditions. The homogeneous still has an impact because of what happens when you plug in time equals 0. Because even though it's in steady state, that's dependent on the external force, the natural frequency must have an impact on the response. If I change the spring, it can't have the same exact response. It's going to be different. It has to be. So there has to be some term there. So now what we'll do for this problem is they told us the initial conditions were 0. We'll say that x total. This will be this term minus this term times sine omega t. Minus times sine. Oh, sorry. That's not correct. They're different signs. Sorry, guys. What am I doing? Let's just write it out fully. impact or anything. So the term due to the driving frequency minus the term due to the natural frequency of the system. And that's our total response. You can now plug in all your variables. You can plug in 0.112 for F naught, you can plug in omega n, 0.968 for the natural frequency. What was omega? 10. That's based on this. This is omega. And if you do all that, you get 0.0117 sine of 0.968 t, unless I flip the signs around. Oh, I did. I wrote it backwards in my solution. Well, we'll write this one first, sorry. This is negative, my solution's definitely wrong. The signs are all messed up. But you can plug in the numbers and get what your answer is from that. I don't have the exact answer. My solution's wrong. I have to fix it.
You could do it.
Can you exactly?
I don't want to do it. If you want to do it, go for it. You can
No,
tell
I
me.
wanted you to do it.
You want me to do it?
Yes.
Oh my god.
Thank you.
I need a calculator.
Here, you could use mine.
What's this fancy?
I have another one.
Recitation.
Put the other ones in the back.
Do you want this one instead?
What I do want is my PI 30XA. Minus omega squared. Divided by F
I
naught.
have all my fluids.
She's busted,
I
man.
got my laptop somewhere.
Yeah,
I got
That's what I'm saying.
He makes us use, he made us use
my laptop fell off.
I use that calculator all the time, the one from ComPactor. That's my favorite calculator, right?
Why?
calculators.
I don't know, I've just gotten used to it. It's fast.
No, it's not.
What's he yapping about?
You said that I calculated.
Somebody double check my math that this is correct,
Yeah.
please.
Yeah.
Yeah, I just think you should.
I think you're right.
Homework, to be honest.
Why?
You're really struggling, you know. I just.
So I don't give you numbers on exams.
Peter is struggling, but I'm gonna struggle.
Peter said he
Divided by
was spraying his hair.
0.968 plus 0.0117
So I could just take
times
pictures.
0.968. Oh, that does match my notes, okay. You know why I got confused? I was looking at these signs, but this omega minus omega n, if you look at the frequencies, we are driving past resonance. Resonance is less than 1, we're driving at 10. So this ends up becoming negative, which is why I got confused when I was looking at the notes stupidly.
How dare you?
No, you're good.
I know. How can I get confused? Okay,
It's a Friday.
that's the question we did. Check.
So since X naught and V naught are both 0, does that mean the displacement is mainly dependent on the force?
Yeah, that's correct. It's only dependent on the force. Because again, if you look at this, at time equals 0, it hasn't moved, right? The signs go away. But at some time later, both of these terms depend on the force. If F naught was 0, there'd be no motion. So all the motion in this problem depends on the force. What else? We can stop whenever you guys want. I don't care. It's up to you guys.
You wanna go over electrical systems?
Hell no.
Or heat transfer? No.
That I'm not able to help you with. I can get Pirtle in here that I can call Frank up. and be like,
Bro,
"Yo."
no.
I mean, he is doing numerical methods right now in heat transfer.
Is he? Cool.
What?
What kind of methods?
Finite
It's basically
differences.
central divided difference.
Solid. You guys are learning so much.
It's like nodes inside the wall or whatever.
Like with different materials. Yeah,
No,
like
no,
different
no.
conductance.
Same
Just
material,
no,
but
that's resistances, that's like heat resistance.
That
No,
should- that should-
it's like, you have a point, and then the point above it is a certain temperature, and the left and the
Oh,
right.
wow.
Yeah, no, it's from the
Just
same
other
thing,
than-
it's just worded differently.
He said different materials. It's not
No,
different.
not that. Okay, whatever.
I worded it nicely.
Such a loving family in here. All right. Anything else? Peter?
Got any plans this weekend?
So we're done with class. Cool.
Oh, happy Father's Day.
Damn.
Happy
Um,
Father's Day. Wait.
I might be going to my fiance's family for Father's Day. We'll see.
Oh,
I'm joking. But yeah, if you have questions about things, I'll be here. If you wanna